In this video, we're going to learn about specific different types of waves that we're going to encounter in this class. So the first wave system that we're going to study, and the one that we're going to spend the most time with, is waves on a string or something like a string. So this could be a rope or a cable or, something like that. And I mentioned this in the last video, if you have a string stretched, between 2 points and there's someone standing over here holding one end of it and they move their end up and down, they can make a little wave pulse that travels along the string at some velocity. If they move their arm up and down with a simple harmonic motion, like, sinusoidally, they're going to make a wave, a sinusoidal shaped wave that's going to move along the string that's going to look, something like that. So, a couple things to notice about this. So for this example, where we have this sinusoidal wave on the string, the displacement of the string, like each little piece of this string, is only moving up and down. Now it's hard to see if we can't animate this. It's easier to show this with a demonstration, so apologies. I'll try to find a video that shows this suitably. But each little piece of the string here is not moving left and right at all. Each little piece is only moving up and down. So as the wave travels down the string, this little piece is moving up and down, this little piece is moving up and down, this little piece is moving up and down. They're not moving all up and all down at the same time. They're, undergoing this kind of undulating motion. But the important thing is the displacement of the string is vertical only. And this is true even though the wave is traveling horizontally, right? The wave velocity is horizontal. So our displacement is actually in a different direction to the direction the wave is traveling. These two are perpendicular to each other. And so this means that the wave is what we call transverse. So this just means, transverse here just means the displacement is in the direction, to the side relative to the direction the wave is actually traveling. There are other kinds of waves that are not transverse that are longitudinal, and we'll learn about some of those later. That's where the displacement is in the same direction the wave is traveling. Okay. So, for this string stretched, stretched here, this wave is traveling at some characteristic velocity v. Now, it shouldn't be surprising that this velocity v depends on some details about what's going on with the string. And if we had a little more time and a little more calculus, we could derive this equation. I'm going to give it to you. And if you're really curious where it comes from, you can look it up online. It's basically F equals ma with some extra added on top of it. Anyway, so for a string or rope or cable or whatever, our wave velocity is equal to the square root of the tension divided by a new variable. So this looks like our friction coefficient, but it is not. It is the same letter, mu, but it is our mass per length of the string. So tension we know. So the mass per length here is just a way of saying how thick or how heavy the string is. You could almost call it a density, but we don't mean density mass per volume, that we usually mean when we talk about density. Sometimes this is called the linear mass density of the string. In other words, if you want to know what this value is, if you have a piece of string, measure its length, measure its mass, divide the mass by the length, and there you have it. So mu should be in units of kilograms per meter. F should be in units of newtons. and we'll get our velocity in meters per second. All right. So this is kind of a cool equation. We'll see some examples where we plug in, realistic numbers for tension and mass per length of strings, and you can see that these velocities get remarkably high. For for something like a modest, like a typical piece of string you might have, just like cotton string or whatever, and if you stretch it between your hands, pulling on it just with a moderate amount of force, you can see that the wave velocity in that system can be easily 100 meters per second, which is very, very fast. So that's I don't know, that's pretty cool that you can get velocities that high in such a simple system. Okay, so this is all I want to say about waves on strings now. Transverse waves, and this is our equation. We'll definitely be looking at this system more in the future. All right, let's look at a couple other kinds of waves we have. So we can also have sound waves. So sound waves are pressure waves traveling through air. And we haven't learned about pressure yet, but the idea is, air is a bunch of molecules that can jostle into each other. They're all moving around randomly. And so if I have a bunch of air molecules and I push on these ones right here on this end, I can kind of scrunch some up and make them a little bit denser over here. And when I do that, these denser ones then tend to push into these denser to these over here and make the density over here a little higher, and in the process make the density over here a little lower. So they end up here's like, this is like before and this is after. So there'll be this like region of higher density molecules that moves to the right. I mean, in this case, because I'm like giving them a little push to the right, so this moves to the right. This is a very, very cartoony picture, but hopefully you can kind of see what's going on in your head. Here, our velocity, the wave is traveling to the right, and the displacement, the molecules also traveled to the right. So here our displacement is in the same direction as our velocity, which means this is a longitudinal wave. So not a transverse wave, because these two are in the same direction. The velocity is in the same direction as the displacement. Okay, so for sound waves traveling through air, and I guess I should say this is air at sea level, since as we'll learn more about pressure later in this class, but if you change the pressure significantly, you can potentially change the sound waves also. But anyway, the velocity of these sound waves is given by the following equation, and this is just a what we call an empirical equation. This is an equation we can plug numbers into and find the velocity, but it doesn't tell us anything about where this velocity is coming from. So this velocity is 331 times the square root of our temperature, our air temperature, and this has to be in temperature units of Kelvin divided by 273. And this is going to give us units of meters per second. So, in other words, if we know the temperature, we can plug into this equation and find the velocity of sound waves at room temperature, which is roughly 293 to 298 K. For those of you who know Kelvin, which is hopefully most of you, I guess maybe I should explain that. So to convert a temperature in Celsius to a temperature in Kelvin, we can take that temperature in degrees C and add 273 to it. So if we wanted to know the temperature, or excuse me, if we wanted to know the velocity at 20 degrees C, we would get the temperature in Kelvin by adding that to 273. So we get 293, and then we go 293 divided by 273, and take the square root of that and multiply by 331, and that gives us our velocity at 20 degrees C in meters per second. Okay, so anyway, so at room temperature, if we plug numbers into this, we get roughly 340 meters per second. And this is the number that is most commonly known as the speed of sound. So the speed of sound waves depends a little on temperature and some other things like composition of the gas, and so on. But the typical value that gets used is 340 meters per second. So this is fast, right? This is 700 and something miles per hour. Sound waves travel, very fast. All right. We'll have lots more to say about sound waves later on, but this is at least, this is where we start if we're trying to figure out the velocity. Okay, here's a weird one. Light waves, or really we should call this electromagnetic waves. So electromagnetic waves include things like visible light that we can see. It also includes things like radio waves, and it also includes things like X-rays and gamma rays. These are all different wavelengths, but the same underlying phenomenon. And you'll learn more about this if you take Physics 107. So electromagnetic waves, they are transverse. So I guess, okay, let's start that sentence over. Electromagnetic waves, unlike sound waves and our waves in the string, do not have a medium to travel through in the same sense that the other ones do. So like our string wave is traveling through a piece of string, right? Our sound wave, we can't see the air, but the sound waves are traveling through the air. There's a good demo that we do during in-person lectures where we have a little like mechanical bell and put it in a chamber and suck all the air out of it, and it gets a lot quieter when there's no air. Anyway, so sound waves travel through air. If there's no air, you can't have the sound waves. Light waves, electromagnetic waves, do not need anything. They can travel through the vacuum of space with no matter, with nothing present. And that's because they are traveling, they are displacements of, they are oscillations of this electromagnetic field that, even though there's no stuff in space, this electromagnetic field is there, and so those waves can move through that field. That's all the more we need to worry about that for Physics 106. The unique thing about electromagnetic waves also is their velocity. So when they're traveling through space or through air, places where they have an easy time traveling, their velocity is equal to 3 times 10 to the 8th meters per second. This is the speed of light as it is known. And in fact, this variable is so important in physics, it gets its own letter. This is lowercase c. So speed of light, 3 times 10 to the 8th meters per second. Really fast, and in fact, I think most physicists agree there's reasonable evidence that this is the fastest anything can go ever. So, all right. Of course, you can make light go slower than this, and you'll learn about this in Physics 107. If light goes through something like water or glass, it slows down slower than this, but it cannot speed up faster than this. Anyway, so we'll use this number at some point. I just figured you should see it. All right. So let's talk very briefly about seismic waves. So seismic waves are waves traveling through the Earth itself, the crust and the mantle and the core of the Earth. And seismic waves have a number of different, or actually a collection of multiple different kinds of waves. So you can have seismic waves that are transverse, You can also have seismic waves that are longitudinal. So if I'm remembering correctly, the longitudinal waves are what they call P waves, and S waves are transverse waves. And their velocities depend on what kind of waves they are and what part of the earth they're moving through and so on. But in general, they tend to be fast, I think, in the, definitely in the hundreds of meters per second, if not more. All right. That is all I have to say about seismic waves. Lastly, I want to just mention waves on water. So we also have multiple different kinds of waves in water. And that is, for one, we also can have sound waves traveling through water just the same way they travel through air. Because water has different mechanical properties than air, they travel at a much higher velocity, I think a couple thousand meters per second instead of through air where it's a few hundred meters per second. So those are sound waves traveling through water. We also can have waves on the surface of water, which is more, what we're used to when we think about waves in water. So like down here, this is the water, this is the air. So these waves moving on the surface, these have some properties that are a little different than other kinds of waves we look at. And that is, if our water is shallow, the velocity actually depends on the depth of the water. So if our water is super shallow versus a little shallow versus a little bit deeper, the velocity of these waves changes. The shallower it is, the slower they go, I believe. If our water is very deep, they still don't actually travel at a constant velocity. If the water's very deep, their velocity depends on their wavelength. So the velocity these waves travel can depend on how far apart these wave crests are. And that's all the more I want to say about water waves. We can think of them with some of the same tools, but the rules are more complicated and a little bit beyond what we're going to talk about in 106.